Okay, let's just 1 minute and then we start. Yep. While we wait for 1 minute, you can start to read this. Uh, yes, this is the Indonesian, no, the Indonesian, but this is the English one. Should be the same. Right. Let's wait for 1 minute and then we'll start.
Mm. What? Oh,
All right. So let's start then. Yeah. So today's class, we're gonna use it through Zoom. Yeah, for the penelitian operational or operations research, and we continue with the modeling, and then we will move on to the solution, but graphical solution. Okay, now let's continue with the example of this modeling of a shoe company. Previously, we had a bakery, right? We have another factory, but now this is a shoe company. Okay, so let me read it and let's make the mathematical model for this. Yeah. The shoe company produces two types of shoes. So there are two products. The first is brand I1, which has a rubber sole. The second product is brand 2 or leather soles. So the material is different between product 1 and product 2. Three machines are required to produce those products. Machine 1 makes the rubber sole, machine 2 make the leather soles, and machine 3 make the upper and assemble the upper with the sole. So assembly process, you can say. Okay. Now, each dozen shoes of brand I1 or the rubber sole are initially processed on machine 1 for 2 hours. So it used machine 1 first, the rubber soles, for 2 hours, and then not going to machine 2, but straight to machine 3 for 6 hours for assembly process, right? While shoe brand 2 or the leather soles is not going to machine 1, but goes straight to machine 2 for the first step, 3 hours, and then on machine 3 for assembly for 5 hours, right? So we now know the machine that is used and the configuration of or the production process of those two brand. The maximum working hours per day for machine 1 are 8 hours and machine 2 is 15 hours per day. Okay. And machine 3 is 30 hours. So that means one day is 24 hours. That means this has more than 24. It means it's a set of machines. Okay. Or we can easily per period. Yeah. Which one day is the period and 30 hours is probably means two machine at least. Okay. But same time, machine 3. Yeah. The contribution to profit now. Now we're speaking about profit. For each dozen shoes of brand 1 is 30,000 rupiah. And for brand 2 or the leather one is 50,000. Now, it asks for the problem to determine how many dozen of shoes of brand I1 and I2 on how many should we make for the rubber sole and how many should we make for the leather sole in order to maximize profits. Now, with this, it's easier for us to make a table because we have the data, the production process data. And it's going to be easier if we make a table, right? So here you go. Now, this is in Indonesia, but I can explain to you. This is machine 1 and 2 and 3. This is the brand, medical brand I1, I2, or the rubber and leather. And this is the number of hour that is used for each machine for product type. So say like this product I1, which is the rubber sole, it need to go to machine 1 first for 2 hours, not going to machine 2, but after that, go to machine 3 for 6 hours. And this one, product 2, does not go to machine 1, but go to machine 2 for 3 hours, then continue with the machine 3 for 5 hours to become a dozen of leather shoes. And this is the capacity of working hour. For machine 1's 8 hour to 15 hour, machine 3 is 30 hours, the capacity per day. And this is the profit, which added in here. So for each dozen, it was say what 30,000. It is represented by 3. So in 10,000s, 3 in 10,000, and this is 5 in 10,000s. It's actually 50,000 rupiah. Okay, this is much easier to process and it's going to make you less risk of calculation error. So what should we make? First, we need to make the profit. Yeah, what's the function of profit? Because the number of shoes that we make, or the x1 and x2 as the variable, decision variable, it's connected to the profit. If one dozen of shoes of x1, we'll get 33 or 30,000 rupiah. Yeah, here. So we need to connect the x with the profit. That means should be x1 multiplied with 3 plus x2 multiplied with 5 equal to z. Here, z maximize z equal to 3x1 plus 5x2 in 10,000 rupiah. Yeah, in here, it means that. And the constraint, then you can clearly see that we have limitation of each machine. I mean, this is the constraint and the hour. So machine 1, it's used by product 1. So 2x1 plus 0x2, which is 0, has to be less than or equal 8, like this. Yeah, for the capacity of machine 1 per day. Machine 2, 0x1 plus 3x2 has to be less than or equal 15. This is the capacity. Did you go? The last one is this one. 5x1, 6x1 plus 5x2 less than or equal than 30. Plus this one. See? X1 and x2 has to be same, equal or greater than 0. Okay? Yeah. So if we make a table, it's going to be quite straightforward. The model is going to be straightforward like this. Yeah, so actually this is not so tricky. As long as you can make the table like this correctly. And sometimes we define this table into words in the paragraph that it's long. Yeah, but it's actually not that difficult for this. Okay, this is another example of modeling in linear programming. Okay, up to this point, is there any question?
Program. Maybe share. All good.
If there is no question, then I'll move on to the finding solution using graphical. Okay, so okay, I'm gonna stop share first. And then I'm gonna go to the other PPT. Let me reshare again. Okay. Yeah, I hope I have. Oh, yeah, sorry that it's still in Indonesia, but I will translate to you.
Boy.
Yeah. Now linear programming, but finding solution of the linear programming with the graphical method. Okay. We will also learn about the other method, analytical, which the name is simplex in here, but next week. Yeah, today we're gonna learn about graphical. So I'm gonna translate this, yeah. So graphical method, it's suitable if the problem of the LP or linear programming has only two variables, x1 and x2, no x3, no x4, okay? Then it's gonna be easier with the graph. But if we have more than two, say x1, x2, x3, then it's gonna be more difficult with the graphic, or even if x4, then it's going to be even more difficult. Okay, basically, x1, x2 is a coordinate. Like in a graphic, we have x-axis, y-axis. That means it's actually x1 and x2. Yeah. If it's we have x3, and we might still be able to make the graphic, but that means we have used x-axis, y-axis, and z-axis for x1, x2, and x3. Yeah, even though it's not always like that. Yeah.
Lama anjir.
The mathematical optimization, engineering optimization class. In here we are in a linear.
Yeah.
Okay.
Oh.
Next week. Linear programming to other people, then you need to know optimal solution. Or it's not optimal, normal optimal solution, but it's actually alternative solution. And you gotta know what does it mean. Okay. Right, let's go. First, what does it mean by feasible region? Yeah. Before that, I will need to explain about this graph. Yeah. So basically, this graph is we have x axis as x. Draw it. those equation, and it must be lines because this is linear. So this we have intersect the point of in this line with the other line, then this is what we want to know, this point intersection. Yeah. You connect with these two lines, and the other line is from another constraint. This one also from another constraint. This is actually another line, as a line. This is also a line. From where? From x1 greater than equal to 0, x2 greater than equal to 0. Yeah, if you draw a line, it's like that. And it will shape a region inside this. Yeah, so it will become a closed form, and this is a region, or we call a feasible region, which means a region that satisfies all the constraints. Yeah, which also means all the solutions should be inside this region. All possible. Might be not optimal, but it's still okay. Still satisfy the equations, the model. One of them or some of them might be the optimal one, and that's what you need to find out. Yeah, but not in here, not in this point. Okay, later on I will explain. Feasible region. Yeah, and then we have optimal solution, which is one of or some of the dot or line of those feasible region is the optimal solution, whether it's maximize or minimize. Okay, let's go on. Let's go straight to the example. So now we have the objective function is to maximize z equal to 3x1 plus 5x2 with a constraint or st or subject to x1 is less than or equal to 4, 2x2 is less than or equal to 12, and this one as well, 3x1 plus 2x2 equals less than 18, and this one, non-negative constraint. So just draw this, the constraint. Do not draw this yet. We will, but start with the constraint first. Make the coordinate, the x-axis for x1 and y-axis for x2, and draw all those lines. See here, we have x1 less than 4. 4 is here in x1. So for this equation, we just draw a straight line to the top here. Okay. And then do you write down x1 equal to 4, but then you need to add arrow. Where should it go? Where should it go? Yeah. Because x1 need to be less than 4, that means you need to go to the left, not to the right. Because to go to the right on this area is not feasible. It's more than 4. This is 4 or less than. Okay. So everything in here satisfy the first constraint. Yeah, everything in here satisfy the first constraint. Then let's draw again. The second constraint, 2x2 less than 12. So with this, where is it? This one, yeah. x2 is in it. This line, 2x2 equal to 12. And the arrow pointing to the bottom because 2x2 has to be less than 12, not above 12. So everything in here now, everything in here, not in here anymore. It was fine in here, but now has to be below this. So in here now, the feasible region. Okay, this one. Then we add again. Oh, we have line now, 3x1 plus 2x2 less than 18, or this one. Intersect with the previous line in D and in C. You write down this, 3x1 plus 2x2 equal to 18, and the arrow should point down. It's miss one arrow to go down. This is less than 18, not more. So we have this now. plus this, x1 more than 0, x2 more than 0, that means above this line and around the right side of this line. So this is our feasible region then. Yeah. Now we find the feasible region. The optimal solution must be inside or in the corner point, somewhere in the line of this feasible region. Okay. Now, how can we find feasible region? We will need to draw this now, the objective function. This one, objective function. How can we draw in here? The red one is the one. But how can we make this? And could be in here, could be in here. Just assume z is equal to 3x1 plus 5x2. Just pick a number, a z, that is the lowest multiplication of this. That it still makes sense and easy to calculate integer. Simply make z as 15, for example. If z is 15, 15 equal to 3x1 plus 5x2, how can we draw it? Let's draw. If x1 is 0, this is 0. So 15 equal to 5x2, that means x2 is 3. 3. I'm going to cut in this dot. x2 is 3, x1 is 0. Now, the second one, what if x2 is 0? So 15 equal to 3x1. That means x1 is 5. I'm going to cut in x1 5, x2 0 in here. So we take a line, make a line, and this is our initial line of objective function. Okay. Now our next step is to move this line, the objective function, and has to be parallel to the original objective function line that you already made. So you can move either down, left, or up, right, as long as it's still parallel. But where should we move? The goal is to have a max. So move to where it will have the maximum, the highest z. If you move to the bottom, that is actually going to reduce until 0.0, z becomes 0. If x1 and x2 are 0. But if you move until, say, point D, and then you get a number that is the highest, like this, 36 in this case for z, and it turned out in point D, x1 is 2, x2 is 6. This is the highest. Then you have found the optimal solution. Okay, E and C is also a solution. Good enough, but not optimal, not the maximum. Okay, E and C. Okay, this is what it means. Yeah, and this is about the gradient, about the z, because z has some kind of angle, and the gradient of the line is alpha. Yeah, which we will not cover today, but we will cover when we discuss about different way of finding solution, mathematical analysis way, okay? But not now. So let's go back about this angle later. Yeah, in a few weeks, I mean. Okay, any question about this example? Clear? I hope it's still clear, yeah, Ahmed.
All good one.
Okay, let's go then to the second example. But this one now, you need to find the solution. But before that, you need to
Draw.
Make the model first, right? You need to make the model first. Okay. Okay, let me translate. Yeah. So we have a Petty X company produce two type of car or vehicle. Let's say. One is sedan and the other is truck. Okay, sedan and truck. To increase the sales of the company, they will do do a promotion, like advertisement, put their product in an advertisement, a two-way of advertisement, or put in a TV, for example. First is during the film, hiburan, or entertainment, or movie, easily. You put iklan or advertisement during a movie run in a TV channel. The second way is during sport, during football, for example. Just surely you have um, advertisement, yeah, during the rest, within the first and second session or the third one. Yeah. So that's the option where should the promotion or the advertisement is in a show, in a movie, or in a sport, in a football show, in a TV, for example, to make it easy. Yeah. Now, for the advertisement in a movie or at yeah, hiburan, we say it will be viewed by 7 million women and 2 million men. Okay, 7 million women and 2 million men. How come? This is from the survey or from the TV channel. You can choose any channel, but this channel has a survey, and they can see that mostly any promotion, any product advertised in a movie show is going to be watched by women, 7 million women, 2 million men. And then if it's a football show, then it's the other way around. Only 2 million for women that will see, and 12 million men will see, will watch. Okay. Now let's see where where it is going. The cost now, the cost for putting the advertisement in a movie is 5 million rupiah per minute, while putting the advertisement for in a sport or football, it costs 10 million rupiah. Yeah, 10 million rupiah per minute. Okay. Now, if the company wants the advertisement to be seen by at least 28 million women and 24 million men. Now, this is the company. We want at least 28 million women see our product during advertisement, and 24 million for the men. Now, how should the strategy of the advertisement be? The question was just simple, just how is the strategy? Then you need to find out, like, what is the X now? What is the decision variable now? What should define? We have costs, so we probably is going to be reducing costs. Probably, yeah. That's the most sensible understanding. Is okay. We might want to reduce costs, but what contribute to the cost here? 5 million per minute. Look, 5 million rupiah per minute. 10 million rupiah. Sorry, yeah, 10 million rupiah per minute. So it's time. Yeah, it looks like it related to the time, because the more time that we put, more money that we need to pay. We put 2 minutes in the movie show, we're gonna cost 10 million now, right? And if it's in a football show, 2 minutes is going to cost 20 million. So it's not cheap. Okay. It looks like that. Yeah. Based on this is the one that sometimes get tricky. Yeah. What is the extra? That doesn't define anything about decision variable. Just what is the strategy? That's it. You need to figure out what should you find that. Minimus cost, and what related to cost is the the time, while the man and woman is gonna be going to the constraint, because at least 28 women, 28 million women, at least 24 million men. So it looks like this is a constraint. Yeah. So let's just do it then. Here, decision variable, we have x1 is the time advertisement in the film, and x2 is the time for advertisement in the football match, a football show or sports show. And what's the objective function? To minimize z, which is the cost, and we get the cost by calculating x1 as the time with the rupiah, the 5 million per minute. Okay, so if it's 1 minute of x1, we're gonna pay 5 million, which is in 5, okay, in million rupiah. This one also, 1 minute in the football show, we're gonna pay 10 million rupiah, or 10 in million rupiah. Okay, and then we have a constraint in here, which is related to here. How many minimum woman and minimum man should watch? Connected to the
My God.
woman, connected to the man. Yeah, you can see greater than equal to 28, because how many should watch has to be at least 28. And also this one, greater than equal to 24, because men, at least 24 million of men should watch that advertisement that the company put. Okay, and how can we relate this 24 and 28 using this? Okay, there. For each minute of film, it's going to be watched by 7 million of women and 2 million of men. That means, yeah, 7 million of this is the 7 million for women in here, and 2 million of men in here for a football, sorry, movie. While we have, if it's football, we have 2 million of women and 12 million of men. 2 million of women and 12 million of men. So if we now classify this based on the gender, when men and women and men, so we become 7x1 plus 2x2 greater than equal to 28, and this one as well.
Wanita.
Beside x1 and x2, it has to be greater than 0.
Woman. Yeah, woman.
Okay.
Laki.
Any question
Laki.
from modeling of this problem? Clear, yeah? But
Clear, Pak.
okay, but it might not be that clear if you do it on UTS
I don't study.
with a limited time and
Too lazy.
different trickiness. Yeah, so it's good to
Feel like
practice with this or with other
feel like asking
example problem from the internet or from book or
today.
whatever it is. Yeah, linear modeling. Okay, because then the next step after this is to find the solution.
Why
If you have this incorrectly set up the model,
the reason?
then whatever this you calculate in the next step is wrong. Yeah, this has to be correct first.
Huh?
Now, let's draw them. This one, and later on the objective function.
Yes.
This one and this one. This is the first constraint. If we draw the line, is 7x1 plus 2x2 equal to 28, and we need to have more than 28, so the arrow going to the right. And this one is the second constraint, which is 2x1 plus 12x2 equal to 24, and then the arrow is going to go up because it has to be, this side has to be more than or greater than 24. So the feasible region is not going down, but up above these two lines. Plus we have this x1 greater than 0 and x2 greater than 0. But we cannot consider this as a feasible region, because even though this side satisfies the third constraint, doesn't satisfy the first and the second. So we have this above this. We satisfy both, all the constraints. Okay. Then we need to draw the line, objective function line. Z equal to 5x1 plus 10x2. Yeah, draw this line. So you can find just pick a number of z 20, 15, maybe not 15, 20, 30, that you can easily find this. Yeah. For example, this, you got this line, and then you need to, or this line, for example, yeah, from, I don't know what z it is, but then you need to move either to the right, top right, or to the bottom left. Depend on this. Minimize the, oh, to minimize, don't go to the top right, but bottom left. This is getting smaller. Until you find the smallest of this region, which is this dots. This is the optimum, okay, which is the 32 million rupiah. Okay. Any question from this? Clear?
Clear, Pak.
Okay. Now we will need to go to the other Zoom meeting. Sorry, this is only 40 minutes Zoom. So I'm gonna share with you the link. Okay.
Okay, Pak.
Let me copy the invitation to join.
Where is everyone?
Okay. Let's just continue. It should not be too long after this. Yeah. So this is example, and usually this is UTS, so midterm number 1. Yeah.
Okay.
Problem, make the graphical form and find a solution based on that. Then you get the point. Perfect point for this. Yeah. We get Z 32 million rupiah. Yeah. Finish. Okay. But then number 2, there might be another question or different problem that you to understand. Okay. What you should know. Okay. About this different type of solution. Okay. I'm going to translate to you, Ahmed. So this unique finite optimal solution that the problem has only one optimal solution. So what we did before is actually a unique finite optimal solution. Only one. Say this dot is the optimal solution or this dot optimal solution, whether it's close region or open or unbounded region like this. As long as it has only one solution, then it's a unique finite optimal solution. Okay. And then we have this. Oh, this is the example. Yeah. The D is the optimal solution. Okay. And we have what they call alternative finite optimal solution. Instead only one point, we have the whole line now. So everything in this line is the optimal solution. X1 star to X2 star or in between any point in the line is optimal. Okay. Or here. This one is also optimal, even though it's like, optimal. This is called alternative optimal, but this one is like almost unlimited. Not almost unlimited, but you can just choose this X dot, no, sorry, X star instead of the unlimited point somewhere because it's gonna have same Z. This one same Z. You put this point, you put this point, or this point in here, and you put in the equation of the objective function, the Z is going to be the same, including this point, or somewhere unlimited. Yeah, it's still going to be the same Z as if it's for the X star. Okay, right? This is alternative final, almost solution. Okay. The thing is with this, then you have several options. Here's several options. Yeah. All this line is the option. So where should it be? If you present this to the manager, for example, he will ask you back. So where should we put? What configuration should we have? For the X1, X2, we have several options. Yeah. Basically, whatever it is in this line is correct. Yeah. Whatever in this line is correct. but which one? Then you can see that which one is the easiest for you to apply. Yeah, or in a factory, because everything applied here is good. You can choose X1 or X2, still same, but which one is easiest to apply? Then you choose the one that's easiest. Yeah, easiest to apply. Yeah. Say if this is a dimension, X1 and X2 is a dimension of a shape of a product. Then X1 is something, maybe this is linear, that means it's not integers, could be like 2.5.6. And X1, X2 is say what? 4.3. You know, you might want to choose 4.3, it's easier. Yeah, you don't have decimal, right? So you might want, okay, let's take the X2 since it's integer, all 4.2 is not decimal, while X1 it has some decimal and probably a bit more difficult to cut if it's decimal. If it's manually cut, for example, manually set up, then you have options. Yeah, there for the alternative finite optimal solution. Okay. Then we have unbounded optimal solution. This is the optimal solution in here, but it's unbounded. So could be fine as long as we have the optimal solution, because sometimes we have not optimal, just unbounded. That means we don't have the optimal one is infinite. Okay. Usually, if like that, we need to add one more constraint at least, like this. For example, this is, I prefer to say unbounded solution, not exactly optimal, but this is the line and the line, the constraint, and the visible region, but it's going way to the top, and the function is to maximize, not minimize. If it's minimized, easy. This is the solution, probably. Yeah. Yeah. But this is maximized to increase until when there is infinite. So for this condition, it show us that, wait, we need to consider one more constraint. We need more constraint. This is unbounded. Yeah, I want to add something, add more consideration somewhere that we can close this area into almost like a triangular shape, almost like that. Okay, that means we need to consider something else that is should be missing. Yeah, and this is also a good thing because the model is basically you are the who creating the model. If you are the scientist or the R&D staff in the company, you're the one who choose the variable. You're the one who choose the parameter, the constraint. So if you see something like this, you should think there should be some other constraint I missed. Yeah, what in what factor, what aspect? Then it's for you before you present this to your manager. Find another discuss about another aspect of the problem, the model. Yeah, like that. Okay, any question from this? All right, let's continue this. Corner point feasible. So here in this region, the one that is feasible is only the corner point. This point, this point, this point, this and this and this. This is another concept. Yeah, if you have a corner point feasible, it's more clear, more smaller option. Because if it's region, then everything in here inside is feasible. But this one is only the corner point that you want to make, that you want to analyze. Yeah, because the other one is not toward the optimality. Okay, the optimal must only be in the corner of the point. Okay. They also have an empty or infeasible. what it means, this is an example. This is an x2, x1. Okay, usually this is x1, this is x2, but just maybe just like the x2 going down to the up, x1 going to the right, and this is constraint line.
Huh?
The second constraint. This is the first constraint,
Chat with her.
and we have this one,
Mm,
the third constraint, which is actually here and going up. So if we want to draw
What is she?
the region, this line going down, so it should be below this line going top left, so it should be above this line is
Si Ike.
to the top,
Ako,
above this line, so above this line for this x1.
yeah,
Looks like this is the region.
she haven't checked.
Yeah, this one I showed my mouse.
Bro,
But then we have
and
this
it's like in the after.
going to the top, not to the bottom, to the top.
It's a waste of
So
time, bro.
for this has to be above
Like,
this,
if she
and we
doesn't
cannot
like
have it because
straight
then it's
answer,
gonna
well,
make
I
the other
do it
constraint
her.
not satisfying, not working.
That's what I hate.
And that this is what we call infeasible. It's not possible to find solution. One part is here, the other part is there, and if you choose here, it's gonna
Agil,
disagree with this condition.
gila.
If you choose here, it's gonna be disagree with this
Oh,
condition.
delay.
Infeasible.
You mean delay?
There is error. If you put this
Agil,
actually
agil.
calculated or even in computer,
Oh,
you
you
will see
mean
an
the
error, infeasible.
subject for.
Okay. So what should we do if this happens? Then again, you need to check
Delay.
if your model is correct.
It,
That means this model is
oh, no,
some
I know,
way
I know.
incorrect, or there
I
is
know.
an
We're waiting for
excess
his for her instruction.
string.
We're functional, but
What
it
if we
don't work
delete this?
anything. Delay, I
Delete
think
this.
it's for
Then it's going to be good. Or we cannot delete this, but
for the time.
we check again, and
Agil
actually the
is
sign is not greater than
we're available,
4,
but not
but less than
working at the moment.
going down. So it's still working too. Still going to be this level because this is below this. Okay.
Yeah, the operator.
So this is also to evaluate yourself, your model, see if it's good enough or if there's some problem with the model. Also for other people, yeah, not just you.
Olivia, bro.
If you
It's
are
the perfect.
more senior in the company, then you might want to help
Yeah,
the junior
perfect, bro.
and see what is the problem, what's the mistake of their problem, okay, or the model, man,
Yeah, she
not
started
the
a
mistake of
Zoom
the
as well,
model. Yeah,
like Google Meet
there,
for us. You know,
there you
like
go. This is some
the
example. Yeah.
laporan, the report.
Any question after this point?
All good, bro. Say, wallahi, wallahi, good.
Do you think it's easy, medium,
It's medium, but
probably just fine? Yeah, I think this should be fine. And this page actually conclude our discussion today. So yeah, it doesn't take much, but actually after this, what you should do is to practice. Yeah, all these are we discuss it together, and might looks easy, but when you actually do it, especially when you do it from the problem, not the model, you need to use make mathematical model. Then there is more challenge into it. Yeah, before finding solution. Okay, there is several example on the internet, on the book. You can try those things